Morning, Syed.
Good morning. How are you?
Not too bad. What about you?
Not bad.
Oh, I forgot to send the assignment grading assignments, but I'll do that later today.
Okay, for assignment 5.
Yeah.
Did you get the email about the students with similar booklets? Okay.
Yeah. Yeah, I'm processing that at the moment.
Okay.
Okay, let's open it up.
Okay.
Morning, everyone. I see some cats are joining us in addition to the usual. We're just about to start. Sorry. My documents aren't loading properly. Okay. Okay, if anyone has any urgent questions that they need to ask before we start, please go ahead. Okay. So
I think I have a question.
yeah,
Fine.
go ahead.
Yeah, so I just wanna like ask about.
Did you raise your hand, by the way, just in case, because
Sorry,
Syed
no.
is
I thought nobody
monitoring.
is.
So next time do that, just
Okay.
because we need to make sure it's controlled. Okay, go ahead.
All right. So like when you give a solution to like an equation set, like what do you give? Like do you write x1 equal to something and x2 equal to something, or you just give like a set of like whatever? Do you understand the question?
No.
Okay, so for example, in the question 5 or 6, and then you are asked to give a solution of the equation set.
Yes.
And what exactly, like what kind of form do you give eventually?
You have to give the set of all solutions.
Yeah, I mean like like do you give like x1 equal to some value and x2 equal to some value, or you give
You have to
something
give a
different?
set of solutions. So you have to present a set, and the elements of that set have to be solutions to the system.
Sorry, can you give an example of that? Like a simple example.
Well, I gave many examples of sets, right? There's many ways of presenting a set. You can say the set of all ordered tuples, satisfying this condition, or you could just write a list, a list of solutions. So you have to ask yourself, what is a solution? What is a solution? Presumably, it's a point in the vector space. It's a vector in the vector space. So you have to give a set of vectors, those vectors being solutions to the system.
Okay, cool. I'll think about it. Thank you.
Okay, so today we're going to talk about something that has been kind of really left behind, because whenever you talk about a certain type of mathematical object, like a group, a ring, a vector space, any kind of mathematical object, okay, any kind of mathematical structure, okay, whenever you discuss it, you have to discuss also how to map between those things. Okay, that's an essential aspect to studying any particular mathematical object. So, for example, we studied sets, and it was very important to study not just what is a set, but what is a map between sets. Okay, and those maps could be of different properties. They could be injective, surjective, or bijective. Okay, so when you study groups, which is not something that we're going to do in this class, you should study maps between groups which preserve the structure, and those maps are called homomorphisms. Okay, when you study rings, you study the maps between rings that preserve the structure. So what do I mean when I say preserve the structure? Well, what is the structure? The structure, remember, the structure of a group is that you have an identity element, you have a multiplication, and you have an identity element, right? So that means that so these are morphisms between mathematical structures, or algebraic structures, if you want to be a bit more specific. Okay, so for example, remember that a group is a set with an operation, multiplication, and also with an identity and with inverses. Okay, remember that that's what a group structure is. It's a set with certain operations. Okay, and so what does that mean? That means that if we have two groups, okay, then what would it mean to have a morphism or a homomorphism from one to the other? Or let's say, I'll call it F. So first of all, it has to be a map of sets. But it has to preserve the structure. So in other words, if I take two group elements in G, and if I multiply them, in G, that's going to give me another element of G. And then I can apply the map. And now this is going to be an H. On the other hand, I could apply the map to the individual elements in G. Okay, those would give me 2 elements in H, and I could apply the multiplication in H to those 2 elements. That would give me an element in H, right? And that should be the same. And it should be that if I take the identity in G, it will be sent to the identity in H, right? And if I have an inverse of an element, and if I apply F to it, that should be the inverse of F applied to the element. Okay, so I'm just giving you an example of what it means for a map of sets to preserve structure. Okay, and so we call this a group homomorphism. Okay, homomorphisms of groups, and whenever we know whenever we know the objects of a type of mathematical structure, like sets, and if we know the morphisms between them, the maps between them, that data together defines what we call a category. Is what we get when considering objects and morphisms between the objects. It's a very kind of high-level idea that captures kind of all these different algebraic structures. So for example, if you consider sets and maps of sets, this is called the category of sets. And if we consider groups and homomorphisms of groups, we have the category of groups. Okay, and what we're going to do today is talk about vector spaces and linear maps. And this is the category of vector spaces. And usually, yeah, that's right. So we need to understand what the natural notion of map is for vector spaces. Okay, so what is it? Well, here's the definition. So a linear map L. So let me just preface this by telling you what V is. So let U and V be vector spaces over the same field F. Okay, then a linear map from U to V is a map of sets preserving the structure, which means that if I take a sum of 2 vectors in U and map it, I should get the same thing as if I map the individual elements and take their sum in V. So U2 is equal to L of U1 plus L of U2. Okay, this is this here is the sum inside U, and this is the sum inside V. So these are 2 different operations, one in one set, one in the other set, but they are related by this mapping. Okay, and not only that, but we also want it to preserve the scalar multiplication. And again, this is the scalar multiplication in U, and this is the scalar multiplication in V. Okay, and this should be for all U, U1, U2 in U, and for all lambda in F. Yeah, these are the conditions. Okay, now I'm taking a little bit of a shortcut here, which everyone always takes, which is that there's more structure in a vector space besides just these two operations. Remember that a vector space has the 0 element. Okay, and so we should say that L of 0 is 0, so that the origin is sent to the origin. And we should also say that additive inverses are sent to additive inverses. Okay, but it's not necessary to require that because those facts follow from these two facts. So for example, it's automatic that L of 0 is equal to 0. And again, this is the 0 inside U, and this is the 0 inside V. Okay, and why is that automatic? Well, it's because, if I take L of 0 plus 0, okay, this should be equal to L of 0 plus L of 0. And this is L of 0. So you can see that whatever L of 0 is, right, it's got to be equal to 0, because here we have additive inverses in V, and we could just cancel one of these, and we would get L of 0 is equal to 0. So this fact implies that L of 0 is equal to 0. But also, for example, if I take L of minus U, right, this is L of minus 1 times U, and this is equal to minus 1 times L of U, right? And so I get minus L of U. So additive inverses are also sent to additive inverses by linear maps. Okay, so it's a relatively easy thing, and even better, just for the people who are even more lazy than I am, you could even write this condition, these pair of conditions, in a single condition. You could say that L of lambda applied to U1 plus U2 is equal to lambda L U1 plus L U2, and this is for all U1, U2, and for all lambda. Okay, so this single condition just captures both at the same time, just by specializing to values of lambda. Okay, so this is just the abstract definition of what is a linear map. It's something that preserves all of the structure of vector spaces that we're talking about. Okay, so before I start to explain this in more detail, are there any questions about this abstract idea of structure preserving maps?
Okay, so Charlie has a question.
Yeah, so when we're defining the category of groups,
yeah,
why is it that the morphism or the morphism between objects in that category is homomorphisms? Like, why can't it be
instead of what?
I don't know, like, because homomorphism is a pretty specific, like.
But instead of what? Instead of what? What do you?
I don't know. I mean, it's. I guess I didn't think that through.
Well, okay. So the point is that whenever you endow a set with a structure, okay, and you endow another set with that same type of structure, right? The whole idea is that you're studying that structure, and so if you have a map between one and the other, you want that structure to be preserved. So the more structure the objects have, the more your maps have to preserve it.
Right. Okay.
So the more constraints there are on the types of maps that you want to consider in that category.
Right. So like a really elaborate object needs to have a really elaborate function to
Well, it's just a function, but it has to satisfy a lot of conditions.
Yeah. So
Yeah.
Yeah. Okay. That makes sense.
It's like social conventions. You know, we have a convention that everyone dresses in clothing, right? And when you go to another house in your society and you map yourself into another person's home, you have to preserve the structure. You need to maintain
Okay.
the social niceties of that society, otherwise you'll be rejected.
Right. Okay. Thanks. That clears it up.
Okay, now, okay, so let me explain some things about this these linear maps. So, okay. Before we get into specific examples, I just want to kind of try to give you some feel for it without you working in any particular example. Okay, suppose that you have a vector space U, and you have a vector space V. Okay, how do I draw them in my mind? I draw them as kind of like an empty space, completely empty space. You don't draw axes because a vector space does not have axes. Okay, there is only one special vector in a vector space, and that vector is the 0 vector. So that's the only one that I draw. Okay. There are certain vector spaces that have preferred axes, like let's say R2, R3, R4, okay? But not all vector spaces are that. We've seen them. We've seen subspaces, which are not coordinate subspaces, that are weirdly inclined inside vector spaces. They have no special vector in principle, okay, except 0. So here is U and V. So my map from U to V, if it's a linear map, it will send the 0 vector to the 0 vector. So there's no mystery about where 0 goes. 0 will go to 0. But if I have a vector, let's say U, okay, then that vector will be sent somewhere. Okay, so where will it be sent? Well, could be sent to any vector. Okay, it could be sent to 0. It could be sent to something non-zero. Okay, let me just assume that we're in a random situation so that it would have to be very lucky for U to be sent to 0. So, oops, sorry, that's not what I meant to write here. This is 0. And this is 0 of U. So where will U be sent? It will be sent somewhere. Let's say F of U. Okay. So how much, if I tell you only that information, if I only tell you that F takes U to F of U in this picture, then what else do you know for free? Well, you certainly will know that if I take, 1/2 U, this vector here, okay, it will be sent to 1/2 of F of U. It will be sent here. And if I ask, what about minus 1/2 of U? Well, that will be sent to minus 1/2 F of U. Okay, so in fact, any vector which lies in the span of U, we know where it will be sent, because any multiple of U will be sent to that same multiple of F of U. Okay, so as long as the vector is in the span of U, we know where it's going. Just because we know one piece of information, which is where one generator, U, the element that defines the span, where it gets sent. So in particular, if U happens to be sent to 0, then everything in the span of U will be sent to 0. Okay, so I'm just telling you this because I want to demonstrate just right off the bat what the power of linear maps is. If you know the value of one element, if you know the value of the map on one element, you're going to know the value on all elements in the span of that element. Okay, so in other words, you get a lot for free when it comes to linear maps. Okay, is it clear what I'm saying when I say that you get a lot for free? Okay, because normally if you have, if I just tell you I have a map of sets, and this one point gets sent over here, you have absolutely no clue where the other points will be sent, any of the other points. Okay, but in the case of a linear map, you know right off the bat that 0 is sent to 0. And then if you know a single value, then you're going to know an entire one-dimensional subspace of values. Okay, now what else do we need to know in order to define this linear map? So far, the data needed, I'm going to write here, the data needed to define f. Okay, first of all, we needed to specify where is u sent. So u is sent to f of u. Okay, and now in order to give you more information, I should pick another vector and tell you where it's sent. Now, there's no sense in picking a vector which is already in the span of u. So I should choose a vector which is linearly independent from u. So I choose another vector, v, or let's say u2. Okay, let's say this was u1. Okay, and now I have u2. So number 2, u2 linearly independent from u1. u2 sent to f of u2. So where is u2 sent? It will be sent to, let's say, f, let me write it underneath, f of u2. Okay, so that's the second piece of data that I provide for you. Okay, I tell you where u2 is sent. Now, as soon as you know u2, you're going to know all scalar multiples of u2. So that means that for sure you're going to know automatically right off the bat where all these span is sent. It will be sent exactly to this line, which, by the way, could be 0. In this, if you happen to be really unlucky and u2 is sent to 0, then everything in the span of u2 will be sent to 0. Okay, so far we know the value of the linear map on a line and on another line. Okay, but here comes, so what have I used so far? What I've used is just this property, the property of scalar preservation. Okay, but there's also this property. This one is extremely powerful. It says that now if I take a vector like this one, let's say, oops, sorry, that's the wrong. If I take this vector, u1 plus u2, I'm already going to know where that is sent. That will be sent for sure to this one. Okay, so in other words, what's happening is that you have this, and the same thing is true for all the points in the plane, right? Any point at all can be expressed as a scalar multiple of u1 plus a scalar multiple of u2, right? And we know that u1 is sent here, and we know that u2 is sent here. So if I have this, which is like 1.1 u1 minus u2, that's going to be sent to 1.1 f of u1 minus f of u2. So what's that going to look like? It's going to be a little bit bigger than f of u1, and then with a minus f of u2, so it's going to be sent here. So this is going to be f of p. If this was p, then f of p will be sent there. So basically all these points will be sent to all these points. So just by knowing these two pieces of data, knowing only where u1 and u2 are sent, we know where any vector v in the span of u1, u2 is sent. Okay, so this is the important thing. So what's the conclusion to this? The question is, how much data do you really need in order to know the map completely? Well, anyone want to hazard a guess? So what's the amount of information that you need?
So you would want to know where the elements of a basis are sent. Like if you're
I can't tell
considering
who's
the entire.
answered. Who is it?
Yeah, it's Yash. Wait, I'll start my video.
Okay.
Yeah,
So,
yeah.
so
So if
what
you
do you
know,
need to know?
yeah, so if you know where the elements of the basis of the vector space are sent, then you know where the vectors of the entire vector space are sent.
Right. Okay. Thank you. So keep using the hand up feature, because we don't want to. Yeah, I'm just afraid that
Yeah, okay.
people are getting sloppy. Okay. So so thank you. So if we know, so if B En is a basis for U, let's say, and we know the values f of E1 and f of En, that's n pieces of data, then we know all possible values. An infinite number, potentially, depending on how big your field is, you'll potentially already automatically know an infinite number of points. So here's an example. Let's suppose that you're in 3-dimensional space, right? And you want to describe a rotation of space. Well, one way to describe rotations is to specify an axis. So we choose a line in 3-dimensional space. Okay, and there's your line. So this is a line in 3D. Okay. And then you choose an angle and you say that I want to do a rotation around this axis by a certain angle. So, oops. So then you choose an angle. So let me just say that there is a certain angle here, theta. Okay, which is between, let's say, 0 and 2 pi. And you rotate. Okay, and keep in mind that you need to have some convention about in which direction you rotate. So that's why I'm going to put an arrow head on the line. So you choose a direction on the line, okay, and that tells you, and then we decide that we're going to use the right-hand rule, which says that you're going to rotate in a specific direction, the one that I drew, okay, that goes around, and you rotate by theta. Okay, so this idea of a rotation, you can see that if I take a vector, take any vector at all, say this one, okay, then if I rotate it, okay, I'll get, let me call the rotation R L theta. It depends on this axis, this line, and an angle theta. Okay, and if you take R applied to, let's say, U1 plus U2, okay, you can convince yourself, and we're going to see in greater detail later, but you can convince yourself that if I take if I take two vectors and take their sum, and then if I rotate the two vectors individually and take their sum afterwards, okay, what I'll get is the same thing. And also that if I take a vector and scale it, then I'm just going to get the scale of the rotation of the original vector. So rotations are perfect examples of linear maps. Okay, as long as the only thing I didn't mention here is that, let's say that I mean, three-dimensional space doesn't have a specific origin, but in R3, we definitely do. So let's assume that it's a three-dimensional vector space and that the axis is passing through 0. Okay, and then we're okay. Okay, so three-dimensional rotations are linear maps from the space to itself. So we'll see this in greater detail later. Rotations are linear maps from R3 to R3. Okay, and there's many rotations. Depending on which axis you choose and depending on what angle you choose, there's plenty and plenty of rotations, and they form an infinite set of possible rotations. Okay. I mean, we're going to see many examples of rotations, but I just want to get the important ones out of the way. So suppose, so this is not the most perfect example, but it is a very important example to keep in mind. Actually, you were asked to read, I guess, this chapter which describes linear maps. So it shouldn't be the first time you see it. Okay, but let me give an example which you probably didn't see in the reading. So another example. Suppose that you have a factory, and this one is surprisingly confusing. So let's say you have a factory, and this factory, as most factories are, they can produce several different types of goods. It can produce several products. Let's say P1 up to Pn. So there's a list of products that this factory can produce. Okay, and so that's the stuff that comes out of the factory. You know, on Monday this product is coming out. On Tuesday this other product. It could be cars. It could be cars and trucks, and maybe there's several models of different car that the factory produces. Okay, but what goes into the factory besides people and energy is ingredients, like main ingredients, like metals, car parts, wheels. There's ingredients needed, right? So materials or ingredients. So this could be primary materials like metals and so on, but whatever, it doesn't really matter. There's certain things that they need in order to make these products. Okay, and so these ingredients, let's call them Q1 up to Qk. Okay, so the factory takes the ingredients and produces the products, right? Okay. And the thing is that the ingredients are common to many of the products. So you might have a factory that makes several models of car, but the metal that they use to make the cars is all the same. So they need that metal for the cars, but right? But the problem is that you know, if you want to make P1, product P1, you may need a certain amount of Q1, a certain amount of Q2, a certain amount of Qk. You may need a certain amount of each of your ingredients. And if you make the second product, you may need the same ingredients, but in a different proportion. Okay, and it's all, you know, it's important to know how much ingredient you're going to need for every different product. This is the same thing. It's exactly the same as a cook or a cookbook, right? There's a bunch of different recipes, and there's a bunch of ingredients. And for all intents and purposes, they're finite. Okay, and the same ingredients, the flour, the eggs, and whatever, they're used for many different recipes, but in different proportion, right? So whenever, you know, so if you think it's counterintuitive, there's a linear map here staring you in the face. What is the linear map? Someone tell me. Please raise your hand.
Charlie?
It'd just be like the cookbook, I think, that you mentioned, like the list.
So what does the map do? It takes what to what?
It takes one product and it gives you the required ingredients that you need.
Yes.
For.
Yes, that's
I
correct.
think I got it right.
Okay, so so the reason that I say that it's counterintuitive is because the factory takes the ingredients and produces the product. Okay, but that's not the direction that the map is. The map is in reverse. The map starts with the product and figures out what the ingredients were that you needed to make it. So there is a linear, roughly speaking, map from what? From R to the from R to the N, okay, which we'll think of as the span of the products. Okay, so we're going to think that P1 corresponds to the vector 1, 0, 0, and P2 corresponds to 0, 1, 0, 0, and Pn corresponds to 0, 0, 1. Okay, 2, Rk, which is the span of the ingredients. Okay, where again, we're going to think that Q1 is 1 and so on up to Qk. So we have Rn going to Rk, and this is the factory F. Okay, and the idea is, well, okay, I mean, actually it's not entirely true, right? There's a lot of waste and so on in factories. So it's not purely efficient like this. You cannot expect that you need exactly double the ingredients to make exactly double the number of cars. Or, you know what I mean? Like you cannot expect not to have any losses, but nevertheless, roughly speaking, the amount of ingredients you need is proportional to the amount of output, right? And this is different from, let's say, an academic institution. Like in an academic institution, like a university, it's nonlinear. So if you, the products are all the research output and the students' output, degrees and so on, and the research and the input is basically money, I guess. You put money into all of the people and they produce research, right? Or coffee, they say. You put coffee in and the theorems come out. Okay, but just because, so if you give me twice as much coffee or 3 times as much coffee or even 5 times as much money, I'm not going to prove 5 times the number of theorems. It doesn't work that way. So it's a nonlinear system. The output is not proportional to the input. Okay. Any question about this this example? No questions? Okay.
So Long Tai has a question.
Okay, go ahead.
What is real like R to the power of N and R to the power of K represents again? It just it's not real numbers, is it? I don't think. It means the span of products.
This is the real numbers, yeah. I just mean, you see, I understand why this is confusing, because I'm saying that there's a linear map. So yeah, thank you for your question. So think about what I'm saying. It's a little bit confusing. I'm saying that there's a linear map from the products to the ingredients, but I didn't say what the vector spaces are, right? Do the products form a vector space? Well, I mean, the products are, they roughly speaking form a vector space in the sense that, I could ask you the problem, I want to make, a car model. I want to make a Model 1, a Model T car, right? And I want to make 3 Model R cars. So that's my request. I'm requesting 1 model T and 3 model Rs. So that would be like the vector 1, 3. Okay. So you can't really produce 1/2 of a car. So that's why I'm saying this is not a perfect example. But if you ignore that for the moment, and you just imagine that your factory can in fact produce half a car or a third of a car, then that means that the products can be thought of as vectors with real entries. So you can produce a square root 2 of a car. I mean, that's not the, there's better examples that are more precise, but this is an interesting example which actually is part of the origin of linear algebra when they were doing it in World War II. You could imagine that the factory, right, has all these products and it has all these inputs, but the inputs were produced by another factory, and that factory had other inputs and so on, right? So you have a sequence of factories, each one of them taking inputs and producing outputs. Then the next factory takes those outputs and produces another output, right? And each factory is basically operating as a linear map. And then you're in the end, you kind of want to know, I need 100,000 tanks, or I need 50,000 tanks. How much metal do I need to mine? How much tin, copper, and so on do I need to mine? So I need to compute the composition of all these linear maps to know, for this number of tanks and this number of machine guns and this number of, soldier uniforms, how many ingredients do I need to mine, right? And that's what I'm saying, is that that's roughly a linear algebra problem. It's not perfectly a linear algebra problem because no one was going to ask you for square root 2 number of tanks. Okay, but hopefully you understand what I'm trying to convey.
All right.
Any other question about this? Okay. And by the way, for those of you who are interested in machine learning and artificial intelligence, neural networks are exactly like this. A neural network is a bunch of layers, and each layer takes inputs to outputs. And then those outputs are sent to another layer, and they take them to outputs, and so on. So in a way, when we have a bunch of factories, one producing things that the previous one produced, right? If you have a stack of these factories, right? That's very similar to a neural network. Anyway, sorry for those people who have no clue what I'm talking about. Just forget what I just said. Okay, let's go back to linear maps. So before we, actually, let's go to break now. And yeah, let's go to break. We'll be back in 10 minutes at 12:06.
No question today?
No, I'll take questions after.
I meant quiz.
Oops. Okay. Are we back? All right. Okay, rotations, factories. So far, so good. Okay, so let's do a quiz. No surprise. I am. Let's see. Okay, so you have 5 minutes. So set a timer, or write down the time or something. Okay. Go ahead.
Professor, how much time left?
We're at 4 minutes, 10 seconds. So there's a minute left. Okay, everyone enter your final answers. I'm about to close the quiz. Come on. Yeah. Only 10 people left. Let's go. You're living dangerously, you guys. Come on. You should be logged on using your real name, by the way. It would not be a wise idea to log into an official class without using your actual name. Okay, I am now ending the poll, but there's 7 people who haven't answered yet. Can you please Okay. Okay, so we have the results. So take a look at this. So try to take a screen cap or something and then make sure that you ask these questions on the Piazza. If you don't understand them, because I chose them to be extremely simple. Okay, so the first question is asking about whether a list of length 4 is linearly independent, but we're in a 3-dimensional vector space. So we know that the length of a linearly independent list has a maximum length. The maximum length is the dimension. That's stuff what we covered last week. So because the dimension is 3, the maximum length of a linearly independent list would be 3. So because it has length 4 right away, you know that it cannot be linearly independent. There must be a redundancy between those 4 vectors. Okay, next one. If we have F3, again, it's a 3-dimensional space. Is it possible to have 2 subspaces of dimension 1 which intersect only in the 0 vector? So, you know, with a question like this, okay, one way to think about it is that you have 3-dimensional space, you have a line, and then you have another line. So as long as the lines do not intersect, as long as the lines are not the same, okay, then how are they going to intersect? They have to intersect only in a single point. And you could even think about a simple example. You could take the span. Oops, where's my pencil? You could take, for example, the span of 1, 0, 0 and the span of 0, 1, 0. Right? Just pick 2 vectors that are not linearly dependent, take their 2 spans, you get 2 lines, and they intersect only in 0. Okay, and then the next one, now we have a 4-dimensional space in question 3. Okay, so the 4-dimensional space has basis like this, for example. An example would be in R4, you would have vectors like this, right? So if you took these 2 and took their span, and if you took these 2 and took their span, right, then you would have 2 2-dimensional spans. Okay, and they cannot intersect except in 0. Okay, so whenever you're in a dimension n, okay, and this is something that we'll it's actually covered in the reading in great detail, but whenever you have dimension n, let's say 7, for example, you could have a 3-dimensional space and you could have a 4-dimensional space, okay, without having them intersect, because you could take the span of the first 3 basis vectors and then you could take the span of the last 4 basis vectors. Okay, so as long as you can separate them out with linearly independent sets, then you can make sure that this 3D space and this 4D space intersect only in 0. Okay, but if I asked a different question, if it, instead of 3 and 4, if it was 4 and 4, okay, then there's not enough room, there's not enough dimension to have a pair of 4-dimensional spaces which intersect only in 0. Okay, you see here, just, I'm not giving an argument, I didn't ask in the quiz, but the point is that depending on your dimension, there's a kind of, there's only so much room to have completely separate spans. Okay, so that's part of the idea of linearly independent sets. Okay, let me get rid of this. And then the last question, oh no, there's this thing about polynomial. So what's the dimension of the space of polynomials of degree less than or equal to 5? That would be 6. But there's a condition, which is that the 0 value must be 0. So that's telling you that the constant term must be 0. So that means that the coefficients are only the coefficient of x, x squared, x cubed, x4, and x5. So that's 5 dimensions. So it's a 5-dimensional space. It starts off being 6 dimension, but then you put one constraint and it cuts down the dimension to 5. Okay, and then the last question is, what's the dimension of the real vector space of real valued functions on a set? Well, okay, how many elements does the set have? It has 4 elements. And so you're going to have 4 real numbers. So you're going to have R4. So it's 4-dimensional. So the answers are pretty good. The only one that maybe looks troubling to me is the one number 3, which was the hardest question. So that makes sense. Think about it. What I expect you to be able to do is to quickly think of which vectors should I take the span of to get a subspace. Because remember, we have this optimistic way of building subspaces. You just pick a bunch of vectors and take their span. Okay, I'm going to stop sharing it right now. So if you want to copy it down, do it now. Okay, done. Okay. Okay, now, so try to put that out of your mind. And I need to explain something very important, something which causes a lot of confusion, but which is very important. So please pay attention to what I'm about to explain. I'm going to explain linear maps as matrices. So an explicit description of a linear map using matrices. Okay, so I'm going to do it in 2 steps. So the first step, I'm going to try to make it easy by saying, suppose that we had a linear map from Rn to Rk. Okay, so this is the simplest possible case. I mean, like the most easy to think about. Okay, so remember what we just said, that linear maps, they're very, even though that's a map on on a set of size of infinite cardinality, right? There's many, many vectors in R to the n. There's an infinite number. But because of the linear property of the map, because of the fact that sums are sent to sums and scales are sent to scales, okay, what that means is that you only need to know the value of L on a basis. Okay, and if you know it on the basis, then you can work out what the value must be on any other combination of that basis. So, so the question is, what is, so to know to know L completely, we only need its value on a basis. Okay, and well, I mean, there's many bases that you could choose, but for R to the n, there's an obvious nice basis to use. So we're going to use the obvious basis, the natural base, the standard basis. 1, 0, 0, all the way to 0, 0, 0, 1. So it's a basis of size n, of length n. Okay, so what we need, so we would like to know L of E1, L of E2, L of E3. I'm going to give these names, sorry. This is E1. I've discussed this before. And this is En. Okay, so this is what I need to specify. I need to specify the values of L on the basis. And if I know this information, then I will know the map. Okay? And the way that we do this is that we just list the results as columns of an array of numbers. So we just write, this is going to be A1, 1, A1, sorry, A2, 1, A3, 1, all the way down to AK1. Okay, so you have to be careful because there's conventions that are in effect. Okay, these are the standard conventions that we write the results of the linear map on a basis as columns, but we don't change the way that the columns and rows are labeled. Always Roman Catholic or remote control, right? R and C. So here we're going down the row. So the row index is increasing, 1, 2, 3, 4, 5, up to K. The next column will be A1, 2, A2, 2, A3, 2, AK2. Okay, and so on. Okay, so we end up with a K by N matrix representing L. Okay, and now I right away I want to point out something important that first of all, these numbers are in the field. So we have a K by N matrix of numbers Aij in the field, okay? And this is a K by N matrix which represents L, the linear map L, but it's using bases to do that representation. So what do I mean? What I mean is that you need to remember exactly which basis did I use in giving you this information. Well, okay, we're using the standard basis. So in the standard basis of R to the N, but take a look at what I also did. I wrote the result LE1. I wrote it as a column vector of numbers because L maps to RK. So actually this is a vector in RK, right? This thing here is a vector in RK. It's the vector that we get by applying L to E1. But I'm writing that vector, right, as a sequence of numbers because I'm actually, you could think of it as if I'm using a basis for RK as well. Okay, so what's going on is that I have a linear map from Rn to Rk. I just want to confirm that I'm using the standard basis for Rn. I apply L to everything of the standard basis. What I get are vectors in Rk, and then I write the coefficients of those vectors in the standard basis for Rk, and I get numbers. So this is a way of numerically representing a linear map. And then, okay, and then if we, and here's the important thing. So now that we know the value of L on the basis, we can determine all possible values, all values. So for example, so if if x, suppose that we have x1, xn is an arbitrary vector inside, oh, sorry, I was doing r to the n. These are numbers in r, sorry. If this is a vector, a general vector, then we can write x, let's say this is, I'll call it x. We can write x as a linear combination of the basis, right? It's x1 times e1 plus all the way to xn en. Okay. And if I apply L to this, I can use the linearity of L to expand this out. So this will be x1 L of e1 plus all the way to xn L of en, right? So this is, as we expected, the fact that I know L on a basis means that I can figure it out on any other vector. Okay, and what does this look like? So this looks like x1 times this vector a11 ak1. So it's going to be x1 scaling of the result le1 plus xn scaling this vector a1n all the way down to akn. Okay, and this is going to be something in fk, but I'm writing it in a vertical way. I'm writing the list in a vertical way rather than in a horizontal way, okay, just because that's how the convention is that it goes into the matrix. Oops. And okay, and if we want to, I just want to complete this before I take questions. So this this idea usually is written in the following way. You write the matrix A11 okay, and then you write your n-dimensional vector next to it. Okay, so this thing here, this is k by n, and this is n. Okay, so what you see is that so you write the so okay, I'm just trying to explain the conventions, right? The way that people write these things out. So applying L to a vector, I expand the vector out in the basis, and I get these coefficients x1 up to xn. And I need to take a linear combination of these vectors, L of e1, L of en. Okay. Now these vectors, they occur as the columns, the n columns of my matrix. That was the convention, is that I put the values going down, right? And then, so if I want to, so the way that we write this combination, this linear combination, is by just writing the x vector vertically like this. And then you imagine that every row is now you do a dot product between this row and this column. Okay, so what you're going to do is obtain, so this indicates a linear combination of the columns. This should be a linear combination of the columns of, what did I give this a name? Let me call this matrix A. Columns of A with coefficients x1 up to xn. Okay, and how does it look? Well, if you look at the first element, so this is in FK, and I'm going to take the sum. So the first element is going to be x1 a11 plus x2 a12 plus xn a1n. So I'm going to get here a11 x1 plus a12 x2 plus all the way down to a1n xn. Okay, and that's a single number that I put first. Okay, and then I keep going down the list. I use now, so notice that this only used the first row. Now I'm going to go down one, and I'm going to use the second row. I'm going to compute the second row of this. So this is going to be a21 x1, a22 x2, plus a2n xn. And I'm going to continue this way, AK1. Now I'm going to use the last row and this column. AKN xn. So really what this thing looks like is a vector of length k. It's in R to the k. And the what I'm going to get is the first row of A dot product with X. The second row of A dot product with X, all the way down to the last row, the kth row of A dot product with X. I'm just putting a dot there, which means that it's all of the okay, all of the entire row, and maybe just to make it another way of writing it, an alternate form is to write like this, that you could write sum A1, A1j xj, j goes from 1 to n. That's the first element of the column vector. And then we have the next one would be sum j equals 1 to n, a2j xj, and so on, all the way down to a kj xj. J goes from 1 to n. And I get my element in R to the k. Okay, and this is also, this is called, this operation where you take a matrix and a column vector and combine them in this way. This is called multiplying a matrix against a column vector. So it's the product of k by n matrix and a n by 1 matrix to give a k by 1 matrix. But these n by 1 matrix, we just think of it as a column vector. Okay, so again, the convention is very simple. We express vectors as columns, and then we put, when we want to take a linear combination of the columns of the matrix A, we just put the vector on the right side of it, and then we do this dot product of row, column, and you just go down the rows and do dot products like that. Okay, so so this is just explaining the notation for why knowing this matrix of numbers basically tells you how to apply the linear map to any input. This would be any input. I apply this to this and I get my output. Okay, questions about this?
Okay, so Omar, you have a question?
Yeah, hi, Professor.
Hi.
But we haven't exactly defined dot products yet, right? So
this is the expression. So I'm
so
using,
now,
I mean, if you're familiar with the dot product of vectors in R3, right? I'm just giving this a name. It's totally unimportant. The point is this: it's a linear combination, right? This is a linear combination of the columns of this matrix, and I just wrote it out. I just wrote out every component, every coefficient of that linear combination. I just expanded this out. That's all I did. But you should, I'm just pointing out that this column, I mean, this row has length n, and this column has length n, and you're just pairing, you're just multiplying this by this, this by this. As you go down the row, you go down the column, and you just multiply and add, okay? I'm explaining something which should be completely obvious, which is just this. What does this mean? x1 multiplied by this vector. We already discussed what the vector scalar product is in RK. That's what it is, right? And when you work it out, you get this.
Yeah, I'm just like trying to make sure whether or not, like, after this point, dot product is defined or not.
No,
it's not.
I'm just using a term that might be helpful for you, but if you find it in any way confusing, then ignore it completely.
No, but it's not yet defined, and we shouldn't use it that way, right? Because I remember mentioning it once in the tutorial.
Yes. Forget about it.
All right. Thank you.
I don't want to confuse. This is something very important and very simple. Okay. I use the term dot product only to help you, not to confuse you. Okay. I think there's another hand up from Charlie.
So Charlie, go ahead.
Yeah, you were just zoomed in on where you were just zoomed in. It says a element of f to the k. Is that supposed to be f to the k, or is that supposed to be r to the k?
It's r to the k in this example, but everything I said is valid for f.
Okay, just double checking. Great, thank you.
Okay, so okay, now I need to get to something. I need to do this again. I said this was only the first run through. Let's do it properly now. The second run through. Okay, suppose that V and let's say that U and V are vector spaces over the same field. Okay, and suppose that L from U to V is a linear map. If I want to write this explicitly, we want an explicit representation of L. How do we do it? Well, I need to make some choices. Okay, and this is an important thing. We need to be absolutely clear-headed about this. What do we need to choose? So number one, we need to choose a basis BU for U. Okay, so this is important because I know how linear maps work. We just need to know the value of the linear map on a basis, and then we can figure out what the value is on everything else. So that's true. So now suppose that I choose this basis, right? If I apply the linear map to E1, let's say if I do this, what am I going to get? I'm going to get a vector inside V. But V doesn't have axes or anything. So how am I supposed to tell you? How am I supposed to call you up and tell you which vector of V it is that I'm going to get? Well, we need to kind of expand this in terms of a basis of V. So we need to make a second choice, which is a basis of the codomain. BV F1 up to Fk of V. Okay, and it's only in this way, it's only by making these two choices that we can proceed and get a very explicit matrix form for the linear map. Okay, so having made these two choices, we get a matrix of L. So you could call it the matrix of L. Okay, but really, it's really not very helpful to say just the matrix of L. You really need to specify which bases you're using to write the matrix. So it's the matrix of L relative to the basis BU and BV. So it depends on the linear map, the basis of the domain, and the basis of the codomain. It's only with those three pieces of data that you can produce a matrix. And this matrix, let me just highlight it, is defined as follows. So this will be a K by N matrix. So it's going to have N columns and K rows. And the idea is this, that if I take the linear map and I apply it to the jth basis vector, okay, I'm going to put that in the jth column. So in other words, L of EJ, what is L of EJ? Well, it has to be a combination, a linear combination of the basis F1 up to Fk. So this will be some coefficient of F1 plus some coefficient of Fk. Okay, and these coefficients are going to go down the column. Okay, so it's the row that will change. So this will be A1J up to AKJ. Okay, so for each basis vector, so in other words, the formula is this, that if I apply L to the jth basis vector, I'm going to get a combination, okay, and I'm going to put that in the jth column. So the first, entry, maybe you might be confused with how to label this. The clear thing to remember is that the jth basis vector, when you apply the matrix, when you apply the operator, it should go in the jth column. So the second index should be j, okay? And the first index should be summed over. And you have to sum over how many basis vectors there are from 1 to k. Okay, and this is the convention for how the ij entry of the matrix is determined. Okay. Okay. So this is the way that we, this is the convention for writing the matrix. Now, often there's a kind of shorthand which is useful to use. Usually I write this matrix as L, but with a subscript which tells you what the basis for the domain and for the codomain is. So it's useful to do it like this, that L, you put a BU in the front and put a BV in the back, because L, the things that L eats, they're in U, and the thing that it outputs is in V. So you could think of this as the as an alternate notation. For this. Okay, now, so there's an extra thing that I need to do today, but I want to ask about questions for this single page. So if there's anything that's confusing about this, well, I mean, this is always going to be confusing. So you should spend some time thinking about how this thing is set up and make sure that you understand the rules. But if anyone wants to ask a question, you should go ahead now.
Kai, you have a question?
Yeah.
Hi, Professor.
Hi.
Can you briefly explain again how does that alternative notation work?
Well, it's just that if you have a linear operator and you have a basis for the domain and a basis for the codomain, that gives you a matrix, this matrix here. So I'm just giving this matrix a different name. Instead of writing M, L, B, U, B, V, just write L with BU in front. I think of this, by the way, I think of this side as the front of L because L acts on something, right? This is where you put the thing that L acts on.
Okay.
Okay. And so BU is the basis for the domain. And then it it eats stuff and then it ejects it out on the rear side, and that's BV, using the basis BV.
Okay, I see. Okay, thank you.
So you could think of it, think of it that way. Any other questions about this? So maybe let me give an example. So suppose that we have a factory, producing car C1, C2 up to CN with ingredients, raw materials, M1 up to MK. Right. So then what you would write, you would make a grid, so you have, metal 1, metal 2, rubber, and probably mostly plastic, right? And then you have car 1, car 2, car 3, car 4. How much of each do you need? 10 units, 3 units of this metal, copper, and so on. This would be the matrix which maps you from the products to the ingredients. Okay, so you can think that if you took your cookbook and you got rid of all of the useless stuff, like all the photos and all the nice things that people like to look at, and you just cut out those numbers, right? On every page, there's always a list of numbers, which tells you the number of units of the ingredients, right? And you take that list, you just cut it out and you put it down here, right? And you put the next page and the next page, the next page. You could basically make the entire cookbook a single matrix and just give you that. That's it. Okay, questions? Are we okay on this?
Yeah. So Isaac has a question.
Yeah, go ahead.
Yeah, I just want to make sure that I understand it right. So can you scroll back a little bit upward to the matrix? Yeah, I just want to know, make sure. So like the A1s, all the A's are other, say, an arbitrary vector in U, and we've used that A to time the basis with BU, and we got all these numbers, and now we fix these numbers and find another, assume there's another basis which also satisfy these numbers to get a vector, arbitrary vector
I'm
in
going
V.
to stop there because what you're saying, I'm not sure if you're trying to explain this thing again in your own words, but it's extremely confusing. So
yeah, sure.
Let me just say a minimal set of words that explains what's going on. If you're trying to describe a linear map from U to V, okay, what you need to do is to choose a basis for U and choose a basis for V. That's step one. Then you need to tell me where each basis element is sent. Where is L of E1 sent? Where is L of E2 sent? And so on up to L of En. If you know where all of those basis elements are sent, you know everything there is to know about the linear map. The matrix aggregates that information as the columns. That's it. Every column of this matrix is telling you what the value of this is the value of LE1. This is the value of LE2. This is the value of LEN. That's what is captured by this matrix. Okay. The last thing that I should say is, how do I tell you what LE1 is? LE1 is a vector in V, and it should be expanded in its basis. And these are the coefficients. LE1 is a combination of the basis vectors of V, where these are the coefficients going down the first column. L of E2, L of E3, L of En.
Okay. Yeah, thanks.
Okay, Carl, last one. Go ahead.
Yeah, hi. So I saw something in the chat just a bit ago about how the list L of E to the 1 to L of E and may be linearly dependent, and I'm not sure how that's. I might need that to be explained.
Yeah. So the point is that when you have a linear map, okay, so there's always one really interesting linear map that is available to you, which is that L of V is equal to 0 for all V. If you send everything to 0, that's a perfectly good linear map, because if you multiply the inputs by a scalar, or if you add them together, you're always going to be getting 0, 0, 0. So the 0 map is a perfectly good linear map. And so where would L of E1 be sent? It would be sent to 0, 0, 0, 0, 0, 0, 0. The entire matrix would be 0. So these vectors, these n vectors in RK, they could all be 0.
In which case,
that would be, of course, linearly dependent.
Right.
They would span nothing. They would span just the 0 subspace. So there's nothing here that says that the linear map must take a basis into a basis. That's definitely not the case. It could be sent to anything. It could be sent, we could have the same vector being the image of all these vectors. L of E1, L of E2, L of E3, they're all equal to 1, 1, 1, 1, 1. That's possible.
Okay.
You can choose, it's arbitrary. You could choose any vector whatsoever as the value for E1, any other vector for E2, anything. There's no constraint whatsoever. The point is that because this is a basis, that means that if you specify the value on E1, that says nothing about what the value on E2 is. It only tells you what the multiples of E1 must be sent to, right? That's why I developed this in the order that I did. Once you know where L of E1 is, once you know where E1 is sent, right, that tells you where all the vectors in the span of E1 are sent, but it doesn't tell you anything about where the other vectors are sent. They could all be sent to 0, say.
Yeah, okay, that makes sense. Yeah, because I was thinking of the L of E sub 1 to the n, like spanning this whole subspace in itself, but that's not the
It's not necessarily the case. You could have a linear map that sends everything to 0.
It's just telling you information about the linear map itself.
Yeah, exactly.
Okay. Thank you.
Oh, okay. And maybe let me do an example. Okay. Suppose that we have polynomials of degree less than or equal to 2. And we have polynomials of degree less than or equal to 1. Okay. So if I have a polynomial of degree at most 2, I can differentiate it. Okay. And I can differentiate it. And what am I going to get? If I take a polynomial of degree 2 and differentiate it, I will get someone.
Jack?
A polynomial of at most degree 1?
Yeah. I mean, you could have said a polynomial of degree 1,000, of degree at most 1,000. I mean, but you're being very efficient and saying that if the degree was at most 2, then you could say for sure that the derivative of those will be at most 1 of degree. So that means that the derivative operator, d by dx, is a map from here to here, right? It takes a polynomial of degree 2 and it outputs a polynomial of degree 1. Okay, but what kind of a map is it? If I take the sum of a polynomial plus a multiple of some other polynomial where f1, f2 are in P2, and C is in R, right? Then we know that the derivative of a sum of functions is the sum of the derivatives. And if you multiply a function by a constant, then the derivative passes over that constant. Okay, so let me give this derivative a name, d. And what we've proven is that d of u1 plus lambda u2 is equal to d of u1 plus lambda d of u2. In other words, d is a linear map of vector spaces. Okay, it doesn't matter where it came from differentiation. But if we just think about the vector spaces on the domain and on the codomain, then we see that it's a linear map. And so that means it has a matrix. Okay, so what is the matrix? Well, in order to write the matrix of this linear map, I need to choose a basis for the domain and a basis for the codomain. Well, okay, I have a preferred basis for my polynomials. I like the basis 1x x squared for the domain, and I like the basis 1 and x for the codomain. So in order to write a matrix for this thing, okay, I just need to know, I just need to take, so this will be how many possible basis vectors can I feed it? There's 3 possibilities. Each possibility is going to give me 1 column, right? So if I apply the derivative to the first basis element, so let me make a little bit of space. Sorry that I'm going a little bit over. So in the first column, I'm going to put d of 1. In the second column, I'm going to put d of x. In the third column, I'm going to put d of x squared. But I'm going to expand it out using the basis. So I'm writing let me give these names. I'll call this BU. I'll call this B, let's say, and I'll call this B prime. So I'm going to write the matrix using basis B for the domain and B prime for the codomain. And to make this matrix, I just need to put the results of D of 1. So what's the derivative of 1? It's 0. So it's 0 times, remember that B prime is the basis 1x. So it's 0 times 1 plus 0 times x. The derivative of x is equal to 1. And that's 1 times 1 and 0 times x. And the derivative of x squared is 2x, which is 2 times x plus 0 times 1. And so this here is the matrix of the derivative operator using the bases B and B prime. Okay, and it's a 2x3 matrix. Okay, and as a result of this, if I had another polynomial, let's say that I had a polynomial P, which was A times 1 plus B times X plus C times X squared, right? Then if I wanted to know what the derivative of P was, well, then I could write the matrix. I could write the coefficients of P in the basis. So that's A, B, and C. And what I would get is, first I do this row times this column. So I would get 0 times A plus 1 times B plus 0 times C. Let me just, I'm gonna go like this, and like this. Sum them all up, and I'm gonna get A. Okay, and then for the next row, I'm gonna do 0 times A plus 0 times B plus 2 times C. So I'll get 2C. Okay, and if I look at this, if I inspect this and write it as a vector in terms of the basis, it means that I'm taking A times 1 plus 2C times X.
Sorry, I think the first coordinate should be B, not A.
Oh, B, sorry. B and B. I would have noticed that right now when I check this, which is the derivative of this polynomial is this polynomial. So this is dp. Okay, so this is just demonstrating the fact that that all we need to know, because the derivative is a linear map, I just need to know its value on a basis, and then you could figure it out on any other polynomial or any other function that's a linear combination of the basis. So you don't need to pick polynomials as basis. You could pick other functions as basis. Like, for example, cosine, sine. You could take the span of those two functions, and you could produce a two-dimensional vector space based on those two functions. And then you can see that the derivative applied to those basis vectors can be expressed as a sum of cosine and sine again, and you can write the matrix for that. And so you can explore this idea on your own. There's a lot of maps that we use all the time, every day, that are linear maps. And any linear map can be written as a matrix. But the point is that when you do this, it really depends on which bases you use. And if you choose a different basis, you're going to get different numbers. Okay, I'll leave it there. See you on Thursday. And I'll stick around for 5 minutes for questions.
Okay, so Shuji has a question.
Yeah. Go ahead.
Hi, Professor.
Hi.
I have a question about the zero map, the zero linear map.
Yeah.
So you say the linear map preserves the structure two vector spaces, but does the zero map and does the zero vector space and the original vector space have the same structure?
Okay, good. So don't be confused by this this claim, this fact that maps have to preserve structure. Okay, but when we say that they preserve structure, it doesn't mean that they preserve the set itself, right? Remember that a group or a vector space, it's a set with structure, with certain operations. Now, a map of sets, it doesn't have to be a bijection, right? A map of sets could map a whole set into just a single point. That's a possible map.
Yes.
Okay. Now, the original set might have a structure, and the final set might have a structure. And when we say that the structure must be preserved, it means that when you take two elements and combine them using the structure, in the first set, okay, and if you take the results of the map and then combine them in using the structure of the second step, then we should get the same result. So in other words, in diagrams, you should think that, the initial space and the final space could be very different, right? And we could have a map from here to here. But here we have some operation that takes two inputs and produces an output, right? And here we have another operation here. So these are different sets with different operations, okay? But they have the same type. Each of them is a binary operation. It has two inputs and one output. So the idea is that if this point is sent here, and this point is sent here, right? And if this point is sent here, what I'm trying to say is that if I'm trying to compare this combination operation, this binary operation with this one, I want to do the following. I want to say, if I have two input points, I have two possibilities of what I could do with them. I could either combine them in the domain, get a result, a multiplication, and then push that one to the new space using L, right? So I could take one path is to take these two, combine them. That's step one. And then step two would be to send them this way. Okay. But the other possibility is to grab them and not combine them in the domain, but map them directly here. That could be step 1 prime. And then you combine them here using step 2 prime. Right? And those two have to be the same.
Oh, so like.
So preserving structure just means that if you multiply or add two elements and then apply the linear map, what you get is the same thing as applying the linear map to the inputs and then adding the results together.
Oh, I see. So it doesn't have some relationship between two maps. Like it's the structure, it's the operation that.
The operation is the thing that is the structure, and the operation is the thing that is preserved. Right? So a better way to say it maybe is that the linear map is compatible with the operations on the domain plus the codomain. So it doesn't mean that something is the same on either side. It just means that if you apply the operation before or after the map, you get the same result.
Oh, I
so
see.
It's somehow similar to, yeah, it's like
switching the order of operation does not.
Yeah, correct. That's correct. Yeah, you could even say that it means that the operations commute with the linear map. So the order of operation doesn't matter. So it's kind of similar to transferable skills. So it's like if you're an accountant, right? If you are basically able to do certain operations on taxes or numbers, if you're an accountant and you basically represent certain operations, people give you papers of a certain type, and then you process them somehow, and then you output another piece of paper, like the finished taxes, right? That you're like an operator, an operation, right? You take inputs and you have outputs, and you're doing this for a certain company X, but then you could be fired and rehired by another company, right? And that's like a linear map that takes you from IBM to Intel, and it's still fine. They're hiring you to do the same job. You don't need to learn a new operation. The operation that you know is the same here and there, even though the company might be completely different. The size of the company might be different.
Oh, so it's about just like function, not about sets.
Okay, let's go to Omar and Gurmanjot quickly.
Thank you.
You're welcome.
So Omar, I think you're first.
Sorry, no, I from before.
Oh, okay. So Gurmanjot?
Oh, I was just wondering, it's more of a technical question regarding the
Yeah.
quiz. I was
Regarding
just
what?
wondering if the quiz.
Oh.
I was just wondering if we could possibly have quizzes before the break instead of after, because like I ended up missing today's quiz because like I went to the washroom and like I came out a bit later. So I was wondering if it was okay to have quizzes like before the break. So like so like I don't like so it's like so it's like not as like you don't really necessarily miss it if you even if you attend the lecture. Is that possible in any way to accommodate, or did you catch my question? Or
Yeah, I got your question. I think that everyone would probably prefer having the quiz at various different times.
okay.
So maybe it's a better idea to use the break to go on break and then not to go on break during the class. I don't know.
No, I didn't mean
an idea.
Like the thing was that okay.
It's okay.
You know,
I don't want to. I don't want to get into this with you.
It's fine. Yeah.
I'll try my best to not inconvenience you again. But
No, it's fine.
My advice is to just attend the class during the class, and go on break when it's the break time, and leave it at that. I mean, what do you want me to do? There's like 150 people or more in this class.
I know. I'm
can't
sorry. Okay,
accommodate
I was just okay. Got it. Thank you.
Don't worry about it. Okay, cheers. Have a good rest of the week and see you on Thursday.
Really weird request.
Sorry. You. I thought you didn't want to ask your question. Go ahead.
Yeah, it's not actually a question. But we know that you have a reputation for whistling.
What about it?
Yeah. What's it called? I'm asking if it's possible that you one day demonstrate it.
One day.
One day.
One day it'll happen.